In this video, we're going to look at the analysis of some categorical data, and we're going to start off with the usual kind of imports. And we're going to work through this because this may be something you're less familiar with or it's been a while since you've seen it. We're going to work through it basically as a data exploration exercise. So the scenario is that we've got 3 different cities, and people in those cities have been given antibody tests, a certain sample of people randomly selected. And what we're looking for is evidence that the positive antibody tests are more common or less common in certain cities. And hopefully the immediate reaction there is, okay, what's the null hypothesis? The null hypothesis would be that all cities are the same. And specifically, all cities have the same proportion of positive antibody tests. And again, you can think of this in the salesman argument where someone's saying, everything's fine, everything's the same, everything's, Toronto, Vancouver, we'll see those, the cities, they're all dealing the same thing. And you're looking for evidence that that's either believable or clearly not the case. All right, so let's take a look at the data and see what we have. So we're gonna load the data, and there's a little hint later on for what we're gonna do with it, but first thing in any new data set, take a look at the head. And you see, okay, it's got ID numbers, it's got cities and antibody status positives. Now, again, you can do a deeper exploration, though that all looks the same, just by looking at more data. You can open the CSV file. Given how large this data set is, though, I think it makes sense to use some other tools to figure out kind of what's going on. A very handy tool for that is to look at a particular column. And so now we have the names here. We can actually copy that, I think. Perfect. And there's a function in pandas called value counts. You'll see what this does in a second. Oh, it tells us that 185 samples came from Vancouver, Montreal, and Toronto. Another way to have looked at that, if we just wanted to get the cities, is to use the function unique. Actually, I'll leave both of those in there. So you have options, unique. But for what we're doing, actually, the value counts is probably the more helpful one, because it tells us the breakdown of the counts for each of the cities. So we can tell we had a few slightly smaller number of samples taken from Toronto than Vancouver and Montreal. Okay, now let's do that again with the, what was the other title? Let's put our head back in here. And you'll notice that, when I have more than one basic print command, I don't get to see them all. So what we usually would have to do is wrap these things with print statements to guarantee that we're going to get the output. So we do that. All right. So antibody status is the other thing. So if we take a look at that, we have more negatives than positives. Okay, fair enough. What we're interested in, though, is not just negative versus positive, but is it different for the different cities? And that's where we get into what's called a contingency table. So what we're going to do next is refer to a flowchart we're going to find handy. This will be posted on Q. And that's a flowchart that walks you through the kinds of data you have and the most natural or most typical data analysis technique you're going to use. So what we have here is cities. Those are categorical variables. There's only discrete quantities for those. Toronto, Montreal, Vancouver. And the antibody status has only 2 categories to it, negative and positive. So we're into this categorical variable side. And people do use these z-tests, but typically the more general approach is one called the chi-squared test. So this data set would take us on this flowchart to that particular argument or that particular approach to analyzing the data. So with some Googling, you can find out that chi-squared on a contingency table is what we're looking for. And here's the quick help on that. You'll notice right away, it has the classical statistics test of a p-value that's going to come out, and what you're going to put in is an array-like thing, the contingency table. The table contains the observed frequencies, numbers of occurrence, in each category, and it should be a 2-dimensional table. So you can imagine maybe a table of cities and antibody statuses and counts, and well, actually we can do better than imagine it, because there's a lovely tool called crosstab that'll generate this for us. So what we're going to do here is we're going to have our data loaded in, and we're going to build a cross tabulation. This is like an Excel pivot table. So we're going to make a cross tabulation here, and it's pandas, and then it's crosstab, And the nice thing about this, we just give it the data that we want to cross-tabulate around. So we're going to do that. We're going to do cities. Doesn't really matter the order. Actually, it does not matter the order. We'll see how this looks. So we want to basically mix and match cities against antibody status. And we're going to print this so we can actually see the output. And of course, there's an error because I had the equals and everything else in here. So sorry, print. And then we're going to print the data crosstab. Oops. Like so. There we go. Okay, I'm going to hide the other print statements just so we can see the cross-tabulation by itself. And what we get here is, oh, Montreal had 109 negatives and 67 positives. Toronto had 66 negatives, 754 positives. Okay. You can check the counts. Let's put those counts back on for the cities. So we can see that, we need the print statement around that. Vancouver had 185 samples, and now we can see how they broke down. 111 plus 74 is 185. So we know that of the 185 samples, they're broken down to negative positive in this particular ratio, these counts. All right, time to do some stats. So the question is, it's really hard to eyeball this, quite frankly. It feels like there's more negatives than positives in every city, but it's definitely not the same ratio. Like this feels almost the same, whereas this is more. This is where the statistics come in. The null hypothesis is that somebody said the proportions are all the same. So these proportions are all the same. We're asking the question with the statistics, how likely is it to have seen this data if they are right? If these proportions actually are all the same, and we randomly select some stuff, so there's some chance going on, how likely is it that we're going to see this kind of distribution? And here we get to our table calculations, and the vanilla version is just to put in the observed value here. So literally the cross-tabulation, which is the array-like thing, contingency table, table of observed frequencies. Well, that's exactly what we have in our crosstab, so we're going to use that. The things that we get back, sorry, returns, here we are. Chi-squared value, fun if you have a deeper stats course. For now, we're just going to say it's like a Z-score. It's the statistic. It's the thing that comes out that is harder to immediately interpret. However, we do get for free that p-value that we've talked about earlier and a couple of other things. So chi-squared p, d of f, degrees of freedom, and expected values. The p-value and the expected are the ones we're really going to focus on here. So what do we have here? We have the chi-squared, the p-value. I'm actually going to call p-value to make it more explicit. The degrees of freedom and expected equals this. And we just grab our crosstab here. So based on the data we loaded and then tabulated in this way, please tell me under the null hypothesis that everything's basically the same, all the proportions should be equal. What do we get? Well, let's do a print on our p-value here, and let's make it fancy. P-value. Format. There we go. And that's horrible because it's way too many digits. 0.3f. There we go. Perfect. Now just remember the logic here again. P-values are probabilities. So there's a 48% chance that we would see something like this or more extreme non-equal proportions if this was actually the same proportions. And so this p-value is pretty big. 48% chance if the null hypothesis is true, if the story they're telling us is actually the real story. And there's no evidence here that these proportions are out of whack then. So that's our short answer. That exactly tells us what we should conclude here is that we cannot reject the null hypothesis here based on this data. The claim, the null hypothesis, I always think of as a claim or an argument or a sales pitch. The claim that all the cities have the same proportion of positive tests seems reasonable, or is not disproven. Although the double negatives that are everywhere in statistics. And that's really it. Now, if you want to dive a little deeper, what you can do is also print that expected table. So I'll do this in a second cell here. Make that a markdown. And then we're going to do show the expected versus the observed. So if we take a look at the other thing we got back, the expected value here table, It is counts. And what we can do, what typically we'd like to do, is see how different the two tables are. So let's see if that works. No, it wasn't observed, it was crosstab. There we go. So this actually gives us a bit more context. If you take a look at what we observed, so this is our 109, 66, 111, say, and let's put in both actually. We'll print in the expected, and then we'll print this guy. So if the proportions were equal, we would have expected 104. And now it starts to make a little more sense why this is not, why there were no hackles raised, there's no skepticism that you can bring to bear here. No, we expected to see 104 or negative cases in Montreal. We saw 109 with plus or minus 5 out of 100. Yeah, that's not that big a difference. Okay, 67 here. In fact, we can see the differences. This is what the second calculation does. The difference between what we actually saw and what the pure mathematical null hypothesis would have predicted, they're off by 4 or 5 out of 50, 100, that kind of thing. So that difference is not big in the scales that we're talking about. And so the p-value is capturing that for us. It's letting us not have to worry about how big is big. It does that assessment for us. And here the large p-value, 48% chance of seeing this kind of thing or more deviant, is so commonplace. 48%, half the time we would expect to see this kind of variation. So we would say we can't reject the null hypothesis. It seems pretty reasonable that all these cities have the same test results in terms of their positive and negative proportions for the antibody. And that's the gist of it. When we're talking about the quantitative measurements, the value counts are the main thing that we get out of that. So with this kind of code, we can do some straightforward data exploration of categorical variables and then perform an analysis of whether the proportions in that data are actually consistent between different categories. And so that gives us a reasonable start on statistical analysis for categorical data.